on this slide is a IR spectrum. And what we want to talk about is the y and the x-axis and understand what this orange line, all these scribbles really, what it means. Believe it or not, all this information right here helps chemists determine the structure of molecules. It's going to be so cool once you've learned how to interpret what this is actually saying. It's pretty neat. So the y-axis is in transmittance, percent transmittance. So when we take our sample and stick it on the IR instrument, we are monitoring how much of the light goes straight through our sample versus getting absorbed by our sample. So what we see here is that about 90 to 100% of the light in this region of space is going right through our sample. Whereas this part right here, you see that it is about 40% transmittance. So a lot of the light is being absorbed by the molecules. So you can look at it by absorption or transmittance. You can look at it both ways. So tracing the pointer, the red pointer here, this is high transmittance, low absorption. Right here on the pointer, at that point right there, we have a small percentage of transmittance, but a very high percentage of absorption. So we're looking at the peaks, and these peaks are when the molecule is absorbing photons of light. Now, the x-axis is in terms of what we call wave numbers. And wave numbers are simply the inverse wavelength right there. So let's write that out. So this little piece right here could also be viewed as 1 over cm. And the centimeters is the size of the wave in centimeters. So we can look at wavelengths in nanometers, meters, any kind of unit. But in IR, they use centimeters, and then we do look at it as an inverse centimeter. So that's the definition of a wave number, is its inverse wave numbers. Inverse centimeters. Now what this does for us is that inverse centimeters also equals this symbol right here, nu bar. So remember that symbol right there is frequency, but when you stick a little bar symbol over there, that is representing the wave number. So I probably should have written it on this side right here. A wave number equals the inverse centimeters of the photons of light. Now I want to go to the whiteboard and write this out. So infrared radiation here has a range is in the range of 800 nanometers to 10 to the 6 nanometers. Okay. Now what I want to do is take a look at that range in wave numbers form. So what we're going to do is we're going to take that and convert it to centimeters. 8.0 times 10 to the negative 5 centimeters. So that's just a simple conversion. We're going from nanometers to centimeters. It's the same number. And if we do the same for that side, we're going to get 0.1 centimeters. Okay? Now, the wave number for each one of these is simply the inverse of it, right? 8.0 centimeters. When you do that calculation, you get this. And if we do the same for this calculation here, we would get 1 over 0.1 centimeter, and that's going to equal 10 inverse centimeters. Right? So that's the range of IR in terms of wave numbers. Now, when we look at wave numbers, the larger the wave number, what does that mean? Well, it's high frequency. And we've learned that energy is proportional to frequency. So if that's high frequency, then this wave number is representing a photon of light that is high in energy. Whereas the wave number on the right is going to be low frequency and low energy when you're comparing these two. But do note that this is in fact the range of IR, but the useful range for organic chemists is from 4,500 to around 400. Right? We don't use the whole IR spectrum. We just use a little snippet of it. Okay. So that is what the IR spectrum looks like, and those are the X and Y axes. Now, there's some other words that we use to describe these absorptions. We use this idea of strong absorptions and weak absorptions. So a strong absorption looks like this. That would be considered a strong. We would also consider that a strong absorption. This one right here would be considered a weak absorption because it has nearly 100% transmittance. And then you could look at this guy right here. You could maybe call that a medium. Like it's all relative when you're comparing the different sizes of peaks. But strong absorptions typically look like these two. Okay. Now, could you argue that one right there may be strong? Yeah, you possibly could. You're not going to be quizzed and tested on distinguishing between this one and that one if they're strong or not. Okay, the comparisons are going to be much more drastic. So if I asked you between those two circle peaks, which one's the strong absorption? Clearly this one. Okay. So those are some classifications that you need to know when it's just learning, like organic chemistry is like learning a new language. There's going to be some terms that you just need to know. Now this slide right here presents some information that's very important, but just reading it to you doesn't, it's not the most effective way of teaching it. So this is kind of just for your study notes. So everything on this slide I'm going to discuss here. And one cool feature about IR spectroscopy is the fact that functional groups, like a ketone right here. So what is the definition of a ketone? That's the generic ketone, right? So when we look at these two ketones right here, oh wait, so that actually, I take that back. This one right here is an aldehyde. Okay. Now what's amazing about the IR is the fact that this carbonyl right here and this carbonyl right here has a unique stretch that is not influenced greatly by what is attached to it. And so this stretch right here on the carbonyl right there versus that carbonyl Look at where they stretch at, right there. Do you see how that the wave numbers 1717 and 1723 are so very similar? And so what this does for us is whenever we have a stretch around 1700, and if it's a strong stretch around 1700, then we know as chemists that our molecule has a carbonyl in it. That strong peak right there doesn't tell us what's attached to it. All it tells us is there is a carbonyl. And that will never change. Doesn't matter what the molecule looks like. Like you could have a 6-membered ring and all sorts of stuff bouncing off here, and all of a sudden you put a carbonyl there. So that carbonyl stretch right there is going to appear around 1700. So that is cool. Okay? The carbonyl stretch will always be around 1700. So what we have here is a table of very common stretches that always show up where we expect them to show up. So look at this. The carbonyl stretches right here. Not that one, sorry. Right there. So we have a carbonyl. It doesn't matter if it's a ketone or aldehyde, ester, carboxylic acid, or an amide. That carbonyl stretch is always going to appear around 1700. You see that? Isn't that cool? Alcohols are going to appear around this range. And then we have this little section in our table here that kind of gives us a description of what it's supposed to look like. And so you see the words used here: broad and strong, medium, weak, all these words to describe all these different types of stretches. And I'm going to go through all of these different stretches and show you examples of them. Okay? So this table is going to prove very useful as you are learning and practicing IR. Okay, so this slide right here introduces another couple terms that are very, very important. And that is what's called the fingerprint region and the functional group region. So we're going to look at a IR spectrum and point out those regions. Okay. Now this right here, okay, is a written form of what I'm going to show you on the next slide. Okay. So that's right here. So let's find ourselves the fingerprint region. Okay. The fingerprint region is about 1400 wave number all the way down to 5, all the way down. Okay. So that region right here is called the fingerprint region. And we call it the fingerprint region because every molecule has a unique set of peaks in that region that identifies it. So it's just like every human being has a fingerprint, and no two fingerprints are exactly alike. It's not possible. Same thing with molecules. No two different molecules will ever have the same fingerprint region. All right? But two molecules could have very, very similar very similar regions in this region from here to here, That region is called the functional group region. So in the functional group region, look at that name. It is identifying functional groups. So if you have two molecules that are completely different, they will have, so if we have, let's say, acetone versus another different type of ketone, the fingerprint regions for these two molecules are going to be completely different, but their functional region in the IR will look very, very similar, because what do we have? We have a carbonyl stretch and a carbonyl stretch. So that carbonyl will show up right there for both of those compounds. Another name for this functional group region is called a diagnostic region. I use those two terms interchangeably. If I say, let's look at the diagnostic region versus the functional group region of the IR, you know what I'm talking about. Okay. Now, in our NMR analysis, or not NMR, sorry, in our IR analysis, we never delve into the fingerprint region. Okay. We just don't worry about it. It's too complex. We don't go there. Our attention is going to be in the diagnostic region, because we need to know what type of functional groups are in our molecule. That's what's very, very important. Okay. So you remember how I circled this right here? All that information is going to be shown on this slide. There's a typo here. So this M should be the letter Q. And letter Q right here represents any heavy atom like carbon, nitrogen, or oxygen. Okay. So in the IR, we have different regions where different stretches appear that help us understand what we have in our molecule. Okay, so in this pink region right here, we would see things like a carbon hydrogen stretch, or a nitrogen hydrogen stretch, or an oxygen hydrogen stretch. That's where we would see those guys. And so a carbon hydrogen stretch is approximately in the range of 2700 to 3300 inverse centimeters. Whereas the nitrogen hydrogen stretch is going to be around 3300 inverse centimeters to 3500. Okay. And alcohols are going to be above 3600. Now you can come back to these tables right here and you can see that's true. That's where I'm getting those numbers. Okay, right there. Okay. So that's in the pink region. That's the type of stretches that you will see. Now, if we go to this yellow region, that's where you're going to find triple bonds. So we could see carbon bonds like that. So we can have the alkyne stretches there. And a unique one also would be nitriles. In the green, we would see our carbon-carbon double bond stretches in there. And we would also see around that region, we would see our carbonyls in that region. Okay. And then in this blue region, we will see single bond stretches between carbon-carbon. Okay. And so that region right there, I don't focus too much attention on that region. And I definitely don't focus any attention over there, because that's further, that's in the, excuse me, I've got to get a drink of water here. That's in the fingerprint region, okay? We can also see that these carbon-carbon bonds right here in the blue is also in the fingerprint region, so we don't look at those, okay? But what's interesting also, in this purple area, that's where we're going to not find stretches anymore. That's where the bending modes start appearing. The in and out of the plane bending modes that we talked about with formaldehyde. Okay, so this is just a good overview of where, when you look at a molecule, where would you expect to find stretches? Okay, so for example, let's do a quick example here. What if I had a molecule that looked like this? Okay, well, I would expect this carbonyl stretch to be around 1700, so in that region. I see a oxygen hydrogen bond, so I'm looking at that stretch right there between the oxygen and the hydrogen. Well, that would be found around this region or over here. And so this slide helps you to be able to zone in at the area that you need to.